Welcome everybody to the second Heidelberg Joint Astronomical Colloquium of this semester. It's my privilege today to introduce this week's speaker, Eduardo Banados. And Eduardo, as many of you know, is leader of the supermassive black hole and galaxies group in the epoch of realization at the Max-Planck-Institut for Astronomy. And he is one of the people who are at the forefront of this exciting new developments in observational developments in the discovery and characterization of the most distant known objects in the universe. And Eduardo did his PhD under the supervision of Fabian Walter at MPIA, and thereafter moved to the US. I think that was in 2015. Where he had he was a Carnegie Princeton Fellow at the observatories of the Carnegie Institute for Science in Pasadena and Department of Astrophysical Sciences, Princeton. And while he was there as a Carnegie Principal Fellow, he was still maintain a pretty close collaboration with MPIA. So he had this synergy where he brought in the US community as well as keeping up the links here, which meant, I think, a very interesting combination, not just of pressing the boundaries of discovering the most distant objects in significant numbers, but also of characterizing them with the multi-wavelength properties. And I think we're going to hear something about that from Eduardo today. So without further ado, I hand the floor to Eduardo to deliver his colloquium entitled The Birth of the First Massive Galaxies and Black Holes. Thanks, Eduardo.
Thank you very much for the nice introduction. My name is Eduardo Banados, and it's my real pleasure to have the opportunity to talk about the birth of the first massive black holes and galaxies to the Heidelberg community. And I think I have two tasks for this particular talk. So if I'm not mistaken, I'm the only speaker in this colloquium series that's going to talk about the high redshift universe. And I think I'm only one of the two local speakers. So my goal is to try to show that the high redshift science in Heidelberg is really at the frontier of what we know. So I know, well, one of the amazing things of Heidelberg is that it has this huge number of astronomers, and it's also very diverse. So it's really, I think, one of the best places to be an astronomer. And because of that, I'm going to try to zoom out, because I know the audience is very broad. So let's start from the very beginning to put this into context. So this is the history of the entire universe, right? So it's all summarized in one slide, the beginning of time on the left and the present day universe on the right. And in this talk, I'm just going to focus on the region that is highlighted here, that is called the epoch of cosmic ray ionization. So this is an important phase on the history of the universe when the whole chemistry of the universe changed from being completely neutral hydrogen to being an ionized universe. All of this happens within the first billion years or the first giga year of the universe, or redshift greater than 6. And this is when the first stars, the first galaxies, the first supermassive black holes start to form. And they are producing the photons that ionize the universe, right? So the astronomical community has put a lot of effort into trying to understand the epoch of ionization, right? So there are important questions here: how the first galaxies, the first stars form. And only until recently, we actually have evidence of objects here that we can study. So as I said, Richard, before, we are really the first generation of human beings able to identify and study some of the first galaxies that form in the universe. And of course, this is not easy, right? So we're trying to study things that are literally at the edge of the universe. So as astronomers, we have been pushing the most powerful telescopes we have and been successful. But I'm just going to show you now examples of the confirmed some of the most distant galaxies we know, like spectroscopically confirmed. So these are two examples of some of really the most distant objects we know in the universe, galaxies. And as you can see here, both in the y-axis you have flux density and the x-axis wavelength. And this is one galaxy redshift 11, the other one's redshift 9. And if you're not an expert in this area, you might have a hard time believing that this is actually true, right? So it's very noisy. This is like an alpha line. So we are really pushing, like these are taken with the most powerful telescopes we have now. I think we have good evidence that these objects are real, but really to study them and characterize them, we need the next generation of telescopes. So it's really amazing that we can find these objects, but to study them, we need the ELT or the James Webb Space Telescope. So indeed, one of the key goals for this next generation telescopes is to actually study those galaxies I just showed you before, but in much more detail, and try to do some of the physics that is impossible with the current data we have. So I'm just going to highlight here that James Webb will play a key role in this. So the ELT as well, but James Webb is just around the corner, right? So it's going to be launched in about a month. And by next year, we should start getting data. So I'm leading one of the programs to do exactly this, to try to characterize some of the galaxies, normal galaxies, star-forming galaxies in the epoch of ionization. Sofia Rojas, a PhD student in my group, is also leading another program to confirm galaxies above redshift 9. So there will be more coming with James Webb, hopefully in a year from now. So stay tuned. And here I'm going to make a parenthesis of my talk, just taking the opportunity that I'm excited about James Webb, and I'm the local Heidelberg speaker for this colloquium series. And I just want to highlight that really we should all be looking forward to James Webb. So hopefully everything will go well in December 18th. And Heidelberg has been really involved in James Webb since the very beginning. So maybe not all of you know this, but some of the instruments or parts of the instruments that James Webb has were built in Heidelberg, like some parts of MIRI and NIRSPEC. Astronomers in Heidelberg, not me, are involved in many science cases. For example, guaranteed time observations. Also, at least one of the early release science programs is led at ARI in Heidelberg. And there are many approved cycle 1 general observing programs led by Heidelberg astronomers. So I think this is going to be really exciting in the next year or so. Just one more slide on this, so just to give you some idea. So of course, the astronomers have been thinking about James Webb program for 2 decades now. So it was really competitive, and the first cycle for proposal was just last year. There were more than 1,000 proposals submitted, 286 were accepted. 24 of them are led by astronomers in Germany. And here I just wanted to, a high fraction of this are led by astronomers in Heidelberg. But here I just wanted to highlight the new generation of astronomers that will be using James Webb. So 25 of those accepted programs are led by students, and this is worldwide, and 2 of them are led by students in Heidelberg. So I think this is really something that we should be proud of, and I think these young scientists have a very promising future, and we should be hearing more about this in the next year. So this is Wuyi Wang at ARI and Sofia Rojas at MPIA. So yeah, so I think we should all be looking forward to this, and I'm sure we will have many more talks about James Webb next year. So coming back to the history of the universe, I wish we could study in more detail the first galaxies now, but as I told you, it's very difficult. And I didn't want to wait for James Webb or the ELT to start understanding the epoch of ionization. So far, my research has been focused on studying the most distant quasars. Still very distant, so in the epoch of ionization, but the advantage of studying quasars, these are some of the most luminous objects we know in the universe, so we can study them in detail even with current facilities. Right, so a quasar is this supermassive black hole that is accreting material, so there's gas, dust, there's fuel falling into this black hole. It forms an accretion disk that goes spiraling around the supermassive black hole. It gets really hot, and that's why these objects are so bright. And just now, as part of the introduction, I just will separate them because this will become more important as part of the story later on, into two kinds of quasars. Quasars that have a very powerful radio emission, or called jet quasars, are called radio loud, and all other objects are called radio quiet. So one more slide to just separate these two objects. So this is a kind of an arbitrary separation that we separate these two objects, these two classes, by radio loudness. So just take the flux density in the radio, divided by the flux density in the UV optical, and if the radio is an order of magnitude higher, we call these objects radio loud. And this is like strong evidence that there must be some powerful jet in this black hole. And if it's smaller than 10, we call this radio quiet, but that doesn't mean that there's no radio emission in these objects. And this has been known for 50 years, right? Since the discovery of the quasars, we know that there's this dichotomy. And since early on, we know that most of the quasars are actually radio quiet, at least up to redshift 6. So 90% of the objects are radio quiet. Only 10% of these objects will show like these very strong radio jets. And this is still an open question. We still don't know why we see this difference. And it's something that we are also actually really interested to try to study. So since I'm going to be talking about quasars for the rest of the talk, I thought it would be good to introduce the topic a bit more. Like, it's very specific right at the beginning. So one of the main messages is like these objects are really complex systems. And to study them, you need a multi-wavelength approach. So these are really, really complex system, and you're probing different physical scales even. So multi-wavelength is key. So this is the typical artistic impression of what one can imagine what a quasar looks like, as a supermassive black hole with this accretion disk in the center of a massive galaxy. And now, if you look at these objects with your favorite X-ray telescope, for example, Chandra, you can see quasars like quasars all the way to redshift 7.5. So these are a real Chandra image of one of the most distant quasars we know. And this is really telling you information very close to the supermassive black hole, the hot corona, and jets. Now, if you observe the same quasar, but now you take an image with your favorite UV optical telescope, now this looks like this. So this red point here is the same quasar, which is 7.5. And this is exactly how we look for these objects. We look for red things, red stars in the sky that we think are quasars. Then we take a spectrum and we confirm them. And now this light is coming mainly from the accretion disk. So this is still probing like really small scales, very close to the supermassive black hole. But this can be thousands of times more luminous than the galaxy where this lives. Now, if you take your favorite spectrograph and point it to this red dot here, you will get something like this. Didn't change, like that. So this is a typical quasar spectrum. We have flux on y-axis, wavelength the x-axis. This is a power law emission that's dominated by the accretion disk. And on top of that, you have these very broad emission lines, carbon 4, carbon 3, magnesium 2. And by studying these lines, we can infer properties of the central supermassive black holes. So yeah, I forgot to say that I'm showing here at the bottom right this spectral energy distribution, just to show that where the main emission is coming from at different wavelengths. So if you study the UV opticals, we're very close to the black hole, but now if we go all the way to the far infrared, the emission is dominated by cold dust or gas coming from the interstellar medium. So this is an ALMA image of the same quasar, which is 7.5. And as you can see now, we are not seeing a point source. This is actually a very extended source with kiloparsec scales, and it's very complex. We believe this is an ongoing galaxy merger. And I won't have a lot of time to talk about the host galaxies of these objects during my talk, but just wanted to emphasize here that these objects are really extreme. If you take the Orion Nebula in the Milky Way, which is one of the most extreme starbursts in our galaxy, and you spread that over kiloparsec scales, right? So these are really, really, really monsters. And now if you go all the way to the radio, and the object happens to have a powerful radio jet, then these jets are really relatively easy to detect with the current radio telescopes. Like this is the radio image on one of the most distant radio sources we know in the universe, which is 6.8, and this takes less than 5 minutes with the VLA. So as you can see, we can study these objects from every wavelength, or even to the most distant objects we currently know. So now that we have an idea of what a quasar is and what different wavelengths tell us about the system, this is going to be the outline of my talk for the rest of the talk. So I'm going to focus on 3 outstanding puzzles or questions. So there are many more things I could talk about, but will require much more time. The first one is the growth of supermassive black holes. Then briefly, I'm going to talk about the state of the intergalactic medium. And at the end of the talk, I'm going to talk about radio quasars at high redshift, and I'm going to connect this with the 2 previous topics. So before we can do anything, before we can do science, of course, we need to know where to look. So we need to find these distant quasars. And this is a really difficult task. These objects are extremely rare. And for finding them, it's really harder than finding a needle in a haystack. So universe is huge, right? And we are looking for very particular systems. And so far, we're only sensitive to the most extreme ones. So for this, we need large sky area surveys like SDSS, quasars, dark energy survey, WISE. So we're lucky that we live in an era where these surveys exist. But really, this is like a data mining problem. We have to remove basically everything to try to find these precious quasars. And this is going to get more interesting in the very near future, because the next generation of large sky area surveys like Euclid, Rubin Observatory, and the Roman Space Telescope will start taking data soon. And this I'm optimistic, so I'm sure that we will find many more quasars. But I'm not going to go into details how we do this. Just have to believe me that we know how to do it. And I'm going to just give you a very quick overview of where we stand in the field, and then try to jump into the science. So what I'm showing here is 2 plots. On the top, you can see redshift versus luminosity, right at the top, faint at the bottom. And the bottom panel is a histogram, so of the known quasars in the first gigayear of the universe. So the community has been looking for these objects for many years. The first quasar in the first billion years was in the year 2000, discovered in the year 2000 by Xiaohui Fan in the SDSS survey. And 10 years later, like, people start to really get excited, like, we're finding these really massive objects very early in the epoch of the universe. More surveys started to look for them. And by 2010, we knew almost 60 of these objects. By 2014, which is when I first published a paper on the discovery of quasars using the Panster survey, we knew about 70. And in the last 5 to 6 years, we have really made a huge progress in this field. And now this plot looks more like this. So all the red points have been discovered from 2015 till today. And there's a big involvement from people in Heidelberg, MPI, in almost all of them. So basically, we have increased the number of quasars in the last 5 years, about 5 times or more, with a big Heidelberg contribution. And this is good because, well, now we have a statistical sample that we can now try to study the population and not just single objects. And really, you can see here that this is the same plot on the left, that there are 3 objects that stand out, that these are like the 3 most distant quasars we know, and the spectrum is on the right, and this is the current frontier. So these are like the objects that set the strongest challenges in our understanding of supermassive black holes in the early universe, and we are trying to understand these objects in detail. So we have also a James Webb Cycle 1 program accepted to study these 3 objects with basically all the instruments in James Webb to have like the most complete characterization of this particular system. So stay tuned to what's coming, hopefully next year. But now that we know we have this quasar, we have more than 300, so we can actually study them, we know where to look. Let's briefly go through these outstanding puzzles. So the growth of supermassive black holes. This is maybe the most challenging question that arose from the discovery of these quasars. Just to give you an idea, so we have this diagram. In the y-axis, we have black hole mass. In the x-axis, the age of the universe and the redshift. So what I'm putting here are real quasars, like black hole mass measurements that we of known quasars. And just to give you an idea here of what we're talking about, at redshift 0, the quasars that we're studying are as massive or similar mass as M87, that is a famous because of this beautiful Event Horizon Telescope image, and the Milky Way is here. So the quasars we are finding and studying are more similar to the M87 than the Milky Way. So why is not a problem? Well, it's not a problem to try to explain M87, because you basically have entire age of the history of the universe to build these objects. It becomes challenging when you find similar objects at higher redshifts, because if you need time to grow these objects. These red lines here are assuming that these most distant quasars are accreting at the Eddington limit, so basically at the maximum theoretical accretion rate that the objects can grow. And you can see that if you go back in time, you need to start from something extremely massive. And this here are some of the most favored theories that are trying, like there are many theories, right? And finding these objects make this challenge even harder. And these are some of the leading theories. So either you have to have a direct collapse black hole in the early universe, or this could be a collision in a 10-star cluster, or a remnant of population 3 of the first metal-free stars. But so we still don't know. Maybe it's a combination of all of them. And when you put some extra constraints here, like when did the first stars form, which is another open question, there are some constraints. Some people have proposed that they should start like around this time. Other studies even later in the epoch of the universe. Then you can see that really it's really hard to form these objects. And this is one of the reasons, one of the most favored current theories is this direct collapse black hole, because it's a big shortcut. Then if you start big, then getting even bigger is not as difficult this time. But still, it's an open question. I'm going to come back to this towards the end of the talk. But this is really one of the main questions in the field. So now let's move to the other outstanding puzzle, the state of intergalactic medium. So there are two, well, there are many things that astronomers don't know. There are, I think, also a lot of things that we know. One of the things that we know for sure is that the universe at some point was completely neutral, and that we now live in a universe ionized. So one of the questions is how this happened. We know more or less when this finished, but exactly the history of this, we still don't know. And quasars have been historically one of the most important proofs of the intergalactic medium. Right? And this is the basic idea. You have a distant object, maybe I need to use my mouse here. You have a distant object in this universe, the light travels towards the Earth, and on its journey, the light has to cross intervening gas, galaxies, and all of that information gets imprinted in the quasar spectrum. So we have a fingerprint of what the universe looks like between us and the quasar. And this is the so-called Lyman alpha forest. So this is a great tool to study the IGM or intergalactic medium, but it's really only useful up to redshift about 5.5, because the universe then starts to become neutral enough. So not even a lot neutral, you just need a tiny fraction of neutral hydrogen to absorb everything blue dwarf Lyman alpha. So if you go to a quasar redshift 6, it looks like this. So you have the Lyman alpha emission line, and then blue dwarf that basically you don't have much more information. So, and this is one of the reasons we know the epoch of reionization has to finish around redshift 6, around redshift 5.5, because then you observe these complete troughs in the quasar spectrum. So one of the main questions here, can we use quasars for IGM studies even beyond redshift 6? We know that we cannot use the Lyman alpha forest, but we really want to get more constraints, because this is really important for simulations. So here I'm showing one simulation that tried to show how the universe goes from neutral to ionized in this redshift range. But there are just many ways to do this. And really we need here observations to put constraints in simulations. So observations and simulations go hand in hand here. And I believe quasars can provide very important input for this. So in the last couple of years, we have demonstrated that quasars above redshift 7 are important, and we can use them actually to put constraints. And this is the called IgM damping wing that I'm not going to go into much detail now because I don't have time, but you have to believe me that when we find quasars above redshift 7, so this is a quasar redshift 7.5, we see a very particular profile near the Lyman alpha line that then we can reverse that and infer how neutral the universe is around this quasar. This particular object, redshift 7.5, we know that the universe is about 50% neutral. So these objects are already providing important information about particular corners of the universe. And so far, in all the quasars above redshift 7 that we have been able to do this study, we see a strong signature of this IgM damping wing. And you need really a strong, a very neutral universe to see this signature. If you go to redshift 6, basically this you couldn't do this. So these are the current constraints that we have coming only from this method. So this is neutral fraction versus time, and these lines you can see here that we are putting some of the first constraints on single objects. So this also tells how patchy the process is, and we really need to find more of these objects to have a comprehensive picture of the process. But and I'm optimistic with the Rubin and Euclid we will find many more, and with the ELT and VLT we will be able to map the epoch of ionization using this technique. But I wanted to highlight another one that hasn't really been used so far, for good reasons. And this is related to radio quasars at high redshift. So now I'm combining this data of the intergalactic medium with quasars that emit strong radio emission. And this is called the 21 centimeters forest. And this has been, this is not a new idea, right? It's been proposed for more than 20 years. And this is analogous to the Lyman alpha forest that I explained before. Again, we cannot study Lyman alpha because it gets completely absorbed redshift greater than 6. But if you use another line of hydrogen, the 21 centimeters, that you can actually detect all the way to redshift, then greater than 10 and beyond in absorption. So this is a simulation of what the SKA will observe if you have a radio source at redshift 10. So in principle, this is doable, and then you have a lot of information on what's happening between the source and us, including the epoch of ionization. So this is really promising. It's been promising for many years. The big problem is you need to have bright background radio sources to be able to do this. And until recently, we didn't have any bright source in the first gigayears of the universe. So just recently, two sources that are bright enough in the radio where you could try to do this experiment have been discovered, one at redshift 5.8 and one at blazar redshift 6.1. So this is great news. So because we have this kind of sources in the early universe, but the redshifts are still like a bit too low, right? So you want really to have these sources at redshift 10 to really exploit the technique. So are we missing radio sources? So what I'm showing here are all the radio sources we know above redshift 5. So as you can see, you can basically count them with maybe with two hands. So this is radio loudness. It tells you how strong the radio emission it is, and redshift. And until recently, we have only these objects that you could do this. And the question is like, actually, why don't we find more? Why there are no more sources within the epoch of ionization, even higher redshifts? So I define myself as optimistic. I think they are there. We haven't found them yet. And only just this year, there have been 3 more radio sources and 2 new redshift records. So in just 1 year, because we're consciously looking for them, and I'm sure there should be more. So and I think this will be important to study the intergalactic medium if we can find more objects like this, even at higher redshifts. So now I will tell you I'm interested in radio quasars for the IGM, but also these radio quasars are interesting on their own. They're really remarkable objects. And there are many puzzles about them. I told you that we don't know why there are 10% of them basically up to the ratio 6. And one of the puzzles that keeps me still awake at night is this, right? So you probably are familiar with these beautiful VLA images of radio jets coming from quasars that can span hundreds of kiloparsecs, right? So these jets can be bigger than the entire galaxy. So they can be really huge. And this is one of the mechanisms that the black hole has to communicate with the environment. But for some reason, we only see them up to redshift 4. So beyond redshift 4, we don't see any radio jet extended on scales of hundreds of kiloparsecs. So why? And then if you ask me, what do we have evidence of extended jets in the first gigayear of the universe? So yes, and these are all of them. So we have only 3. And as you can see, this is redshift 6.1. This is just 200 parsec. This is 500 parsecs. This is the most extended one. It's almost 2 kiloparsec. So they are all very compact. They're nothing like this 100 kiloparsec scale jets. Or one of the questions is why? Maybe they are just very young, so they are still in the expanding. But another possibility, and I think I'm actually very excited about this because we can observationally test it, is that one of the explanations that maybe the CMB is quenching actually this extended radio emission. So this might be a bit complicated, but just summarizing, you go to higher redshift, the CMB gets hotter, right? So it gets hotter in the early universe. The energy density gets proportional, increases with 1 plus e to the 4. So when you go to higher redshift, the energy density of the CMB is high enough that you have more, the photons are moving faster than a lower redshift. And then if you have a lobe, when you have this electron that normally it will just emit synchrotron emission, right? Go through the magnetic field and emit synchrotron emission. At some point, it's more likely that this electron, before radiating via synchrotron, it will inverse Compton scatter a CMB photon. And the net result of that is that instead of seeing the radio emission, this should be seen in X-rays. So perhaps we're just looking in the wrong wavelength. And if you want to see these extended jets, we should look at them in X-rays. But the prediction is that this is really faint for the current X-ray telescopes that we have. But there are other groups, but also we all wanted to test this theory. And this is the theory. So these jets should be even more extended in X-rays. So we designed this project. So as I showed you before, this is one of the most extended radio jets we know in the early universe, redshift 6. So we applied for Chandra to observe this object for 3 days, basically full 3 days. Chandra is one of the most powerful telescopes we have in the X-ray so far. This is indeed the second deepest X-ray observation of a quasar in the epoch of ionization. And the result is still kind of not robust enough, but it still is exciting because we found evidence of X-ray emission that has no other optical or infrared counterpart, well aligned with the jet coming from the DLBA, but 50 kiloparsecs away. So this could be potential evidence that this jet might be extended not only 2 kiloparsecs, but all the way to 50 kiloparsecs. But we still need to prove that this X-ray emission is not coming from a low redshift interloper, and that's the challenge now. But this is really, in principle, could be an exciting result. This could mean that the jet is active for at least 500,000 years. But this result took 3 days in the most powerful telescope we have in X-rays. So really pushing the capabilities of what we can do. And this is also one of the most extreme radio sources we know in the early universe. So really to test this in a more systematic way, we really need the next generation of telescopes like the European Athena or the US or a new X-ray US probe like Axis or Lynx. And in their last week, there was a recommendation to have an X-ray probe that will be something maybe between these two. But this will be really important to really test if these extended X-ray jets are ubiquitous at a high redshift. And I want to come back now to the first question that I told you for the supermassive black hole growth, because I think jets might be important as well. So I show you the same this cartoon already before, where we have black hole mass, age of the universe. Now we take a radial loud quasar redshift 7. This is what you expect, the growth curve accreting at the Eddington limit. What I didn't tell you is that to have this line, this growth curve, you have to assume a radiative efficiency, which is typically assumed to be 10%. So there are good reasons for that. So this is like the efficiency of converting mass to energy. But this does not take into account the conversion of accretion power into kinetic power into a relativistic jet. So if you have a jet, there's an extra efficiency term involved, which actually contributes to make the accretion rate faster, right? So there's a braking effect in the accretion disk that some energy is removed from the system, so you can accrete the material faster having a jet than not having a jet. So jet can speed up the black hole growth and not even violating the Eddington limit. And I think it's important to quantify how common these jets are at high redshift. And I think radio and X-ray will have a key role in the coming years to see this. Because this could also ease many of these other mechanisms how to form a supermassive black hole. So we're in the search to try to quantify how common these jets are in the early universe. And I'm going to finish soon now. And one of the other things that we're doing in my group is that we're really interested in these radio quasars for many reasons, but we are also interested to see how these jets that we see in the universe, that I told you, maybe there are X-ray jets now at this redshift, how do they affect the host galaxies? Are they shaping some of the first massive galaxies in the universe, or they have no effect? So this is still really new. We don't know many of these radio loud quasars at high redshift, but recently we published a detailed study on one of the most powerful radio loud quasars. So this is one of my favorite quasars that you can probably guess, that has this beautiful BLBA radio jet I've shown many times now. And then we observed this same object with ALMA, NOEMA, and the GMRT. And if you want to have more details, please go and read the paper by Sofia Rojas. But the summary is that we are seeing that this jet has an important effect in the properties that we measure in the submillimeter, which is the far infrared rest frame and the rest frame of the quasar. And we have another program ongoing with NOEMA to study more of these objects, and really these jets are having an important effect on shaping some of the first massive galaxies. Again, just to finish, favorite quasar, nice BA jet, and just here I'm going to show an example of how this is affecting the galaxy. And I'm going to zoom out just to emphasize, like, this is beautiful jet, but you need the BLBA. So these are radio telescopes that's spread across the entire world to get a magnificent resolution. And this to put, like, just to give you a more idea how small this is, we're going to zoom out. So this entire square is 1.5 arc second, and this is the BLBA, so it's really, really tiny, the jet. And we propose for ALMA observations to study the C+, so ionized carbon gas in the galaxy at similar resolution, to see if we can see some connection or not in this particular system. And this is what we get with ALMA. So just the same scale. So just by eye, you can see that they look very similar. And this is less than 1 hour with ALMA, right? So this is really not a lot of time. And if you put this together, you can see that they're nicely aligned, and this is still unpublished, so they still work in preparation. But as my understanding is that this is probably the first evidence of radio-driven outflow all the way to redshift 6, showing that the feedback of the AEN is important in shaping some of these first massive galaxies. So I'm going to finish now with a take-home message. So I hope I could convey that over the last few years, we've made huge progress in the field. We now have more than 300 quasars. There's an important Heidelberg role here. And we are trying to solve some of the puzzles, of old puzzles, and then there are new ones arising. I didn't have time to talk about metal enrichment, environments, but we still are trying to understand black hole growth and radio jets and the intergalactic medium, how it changed from neutral to ionized. So there are still many old and new puzzles, and I think there's plenty to do for the next coming years. So, and really this is the start of the full characterization. Now that we have a big sample of these objects, we're really looking forward to push the VLT, ALMA, and hopefully very soon the James Webb capabilities. And in a couple of years now, we will have even more to do with Euclid, Rubin, the ELT, SK, Athena, and maybe some of the next future missions that haven't even started to build, but they will really be revolutionary for this, to try to understand the first sources in the epoch of ionization. And hopefully we can push detailed studies beyond Redshift 8. And I think maybe more important, I hope that you get the feeling that really the high redshift science in Heidelberg is at the frontier of our knowledge, and we're trying to push this even further. Thanks.
Thank you so much for that fascinating insight, I think, into what you've already achieved. I mean, it's quite remarkable how you can actually do multi-wavelength observations of these sources even now, and it's this sort of tantalizing glimpse into the future. I'm sure that there are many questions. I see one already, so I'll ask Andreas.
Yes, so you hear me? Yeah, very, very interesting talk, Eduardo. Mostly about this AGN and their properties at high redshift. But may I come back to the first half of your title, which is called Massive Galaxies. Can you comment on the masses of the galaxies or about the M-sigma relation? Does it hold in a similar way as later, or is it shifted that the galaxies have lower mass?
It's a great question, and I usually have a slide about that in my talks, but I don't even have one in my as a backup slide here. Yeah, I don't have it here. I could, well, the answer is really these are like comparable to the most massive galaxies we know, and now we don't have stellar masses for these objects. We can measure dynamical masses from gas with ALMA and to our bias sample. So we have mass measurement maybe for 20 of the sources. Most of them fall above the line. So there seems to be that the supermassive black holes are overmassive with respect to the local universe. But we are also looking only at the most massive black hole. So there's an intrinsic bias that maybe is not unexpected. One of the approved James Webb programs that was led in Heidelberg, actually I'm not involved in that one, was exactly to try to push this kind of studies to fainter quasars and see if fainter objects will fall in the local relation. But the current picture, the emerging picture, at least with the most massive ones, they seem to be, most of them lie above the local relationship.
Okay, so lie above means factor of 2, 3, or 10? Or?
3 to 5.
Okay.
But I should say, I have a slide on that, which I just, fortunately, I didn't include it here. But I'm happy to, if this is really, and this is for everyone listening, like I'm local, so if you want to talk about this offline, just drop me an email or come to the Königstuhl and we can show you more things that I didn't have time to show in this presentation.
Okay, fine. Thank you.
So another question from Christian Fent.
I'd like to come back to your statement that the jet is changing the mass growth potentially. So what is the idea behind that? I mean, we still have the Eddington limit, you know. So do you talk about disk accretion, that the jet changes the disk structure and that might lead to higher accretion rates, or what is the idea here?
Yeah. So the idea is that you have the accretion disk, and then you have a jet, and the jet is removing some of the energy from the system. So then it makes it easier to things in the accretion disk to fall. So it gets a braking effect on the accretion disk.
I mean, one major thing with the jets or winds is that they remove angular momentum from the disk, and also that leads to a stronger accretion rate, probably. But still, if there's a disk that is hot, you always have this Eddington limit. So
yeah. But
do you know about the field strengths, for example, for these far away sources? Are they different from the jets that are closer? Do you know? Is it
I don't think we can measure that. So, but we assume that they should be similar to the
similar? Okay.
Yeah. But exactly that. So we don't need to break the Eddington limit with this. Just because you lose angular momentum, then it's just easier to accrete. I think this is. I try to say the exact same thing you said. So this is one of right. So trying to solve how to form this supermassive black hole is one of the main questions, and I think if we could do this, would be amazing. I think in the Astro 2020, this US decadal survey, they said this is one of the questions that won't be answered in the next years. But we know that jets exist, and they might have a role, and I think this could be important because we don't need to invoke like some exotic physics. We know these objects are there, these jets exist, and they increase the growth rate naturally.
Okay,
but
sure.
If they are not very common, then maybe this is not a mechanism.
Thanks.
Ralph?
Eduardo, thanks for this very nice overview and these really fantastic observations and data that you presented. So on the very picture that you showed, so you have the direct collapse black hole, dense star clusters, and so on and so forth. I'm actually not sure one needs to distinguish between some of these processes, because I think direct collapse black hole is very difficult to achieve, because on the way you may probably fragment quite a bit and you have naturally a dense star cluster. But if you have a dense star cluster, then you have collisions, and in many cases recent simulations show by people in Concepcion, for instance, but other groups, that that there is then a runaway growth of a single object in the center that then reaches more or less the mass range of what you would get in the old, say, direct black hole scenario. So I think there's quite some progress in recent years which brings together these two, let's say, parts of the black hole channels. And so I was wondering whether you have thought about potential ways to distinguish between the direct black hole channel, the direct collapse channel, and the dense star cluster channel.
Yeah, it's a great question, and I think it's really difficult to do this. I'm not a big fan of the direct collapse black hole scenario, to be honest, because it's just very difficult for this to happen. Like in simulations, you can make it happen, but there has to be very particular conditions. But I think one of the I would be interested to hear more about this study, because I'm not sure if maybe I need to know that put these things together. But if you push this to even higher redshift, then like population 3-star remnant is really almost ruled out unless you have jets that are common.
Yeah, but you never get the starting masses with the POP3 remnants. I think that is completely out. But so, sorry if I continue my question, because what we find when we look at the fragmentation of the direct collapse scenario and then the runaway growth in the dense star cluster, in about 10 to 15, maybe up to 20% of the cases, we do get the binary black hole. And so I'm wondering whether you have ways to separate between a single object and a binary system.
That's a great question. And there's evidence of like at least 30 to 50% of the objects we have are in mergers, in galaxy mergers. So, so probably there are two supermassive black holes there. We don't have the resolution to actually see so far two central sources. For that, you'll need a very high resolution X-ray telescope. But at least the galaxies, like at least 30 to 50% of them are being mergers, and basically all of the radio loud ones are mergers. So I think we have a good sense which might have two AGNs, but still with the current instrumentation, it's hard to tell.
But this would not be from a galaxy merger. So this would really be very, very close pair that then goes through a subsequent accretion history together. But maybe they merge the black holes, but maybe they are still very close together as a binary system. Yeah,
I don't think we have the resolution to do that at the moment. So for that, you probably want to have X-rays. And the better resolution X-ray telescope we have is Chandra, and even there, like it's 1 arc-second. So we're proving 6 kiloparsecs at these redshifts, which is, you probably need something that's higher resolution than that. And I think and Athena, which is the European, has even worse resolution. So I don't think that will be contributing much, but maybe the next generation of the US X-ray telescope could help there, like Axis or Lynx. And actually, I think we should talk more about this, because I think also some people and ETA have in the past predicted that in the vicinity of high redshift quasars might be more likely to have direct collapse black holes. If I correct that, I think it was someone at ETA a long time ago, and because then the quasars itself will provide this background radiation that prevents this gas from fragmenting.
Yeah, that is Bhaskar Agarwal, yes,
Yeah. So I think if we want to find direct collapse black holes, maybe looking in the vicinity of these non-high redshift quasars is the place to go. And I wish this could be in person, because I think that one of the motivations for me to give this talk is to also get to talk to more people in Heidelberg, but hopefully we can have a final opportunity to talk about these things.
I think it would be good to, continue this discussion, maybe.
Yeah.
You're up the hill, we are down here, so I think it should be relatively easy. Okay, thank you.
Thank you, Ralph. I just want to draw people's attention. There are some comments in the chat related to this question of direct collapse versus other mechanisms from Melanie Habudzit. We can discuss this further, I think, after the end of the formal colloquium, because Eduardo has agreed that he can stay on for a few more minutes afterwards before he has to go down the hill. In the meantime, before we thank Eduardo, I think I should just put up, I shall just share my screen.
Let's stop sharing.
Yes, okay. And just advertise next week's talk, which is by David Brain, University of Colorado, and we're going to explore the world of the effect of planetary magnetospheres and planetary magnetic fields on the advent of life on planets. And I think that's going to be quite an interesting different view on the question of habitability of planets that we'll hear next week from Dave Brain. So I can remove my screen sharing. And I think we should all open up our microphones and our videos and thank Eduardo very, very much.